More slides. Mhm. Thank you, Mr. Namban. All protocol observed that day. Like a South African, I have to also say that. And colleagues, welcome to this presentation. It is going to be very short, like I am. But it is open for anyone to make a contribution. It is our meeting and not my meeting. So please let's engage. Tate Namban, the next slide. The next slide, it's about welcome. Tate Namban has done it, but I have my own way also, colleagues. Taking from Chino Achebe in his book, Things Fall Apart, we have this saying, a man who calls his kinsmen to a feast does not do so to save them from starving. They all have food in their own homes. So that means we are now calling you here, not that because you don't need information, you still have information, but we are just trying to update some few things there. When we gather together in the Moonlight Village ground, it is not because of the moon. Every man can see it in his own or her own compound. We come together because it is good for the kinsmen to do so. That is why we are welcoming you in this meeting so that at least we share what we have to share. And then, yeah, that is basically what we have. And then we can see what it is that we are going to have in this presentation. Next slide, Dr. Nambani. As you click, it's difficult because it's having some animations in it, maybe. Okay, now, in essence, this is what is going to happen in this presentation, reminding ourselves and checking if we have done all that is expected of us in preparation for the March test and going forward, colleagues. We are looking at the gaps in the learners' books as we are visiting them, as we are doing curriculum coverage, then we'll be addressing those gaps that we have seen already in the learners' books and what we have seen last year also. That is how we operate. And then the mistake that the learners did, we are going to address that. And then we are also going to look at the recommendations that we are having. So basically, this is the outline of what we are going to be engaging with you today. Next slide, Baba. Now, the next slide, colleagues, it's about the summary of momentum. And I want us to look at, because we have completed momentum. It was done in the first 2 weeks. So I just want to check with you, and you check yourselves as to whether you have maybe address all these bullets that are there. The first one, it is going to look at the momentum itself. And that is the definition. We are going to look at the laws and principles. We look at the change in momentum as a principle that we are operating in. We are also looking at conservation of momentum, and then the examples that are there, looking at the conservation of linear momentum. We are looking at collisions. What is it that we are having, elastic and inelastic? We are also looking at the momentum in terms of Newton's second law, and we are also going to look at the momentum impulse theory, or theorem as we are now calling it. So if you are satisfied that you have covered all this, then I will be happy. But if there are some of the aspect that you are not having covered, then it is going to be what we are looking at that we have to look at. But as we go to the next slide, I just want to find from colleagues, if a learner just ask you, what is momentum? Are we in position to can talk to what is momentum? Because usually we'll be saying when the learners are doing good, And keep the momentum. Are we also talking at that particular instance of momentum, loosely so as a language, that we are talking to the explanation that it is not in essence, what is it that it is in physical sciences? So I want us maybe to have a look at it and just check with yourselves as to whether are we in the same wavelength, that we are not really explaining what momentum is, but most of the time we are defining momentum. And as such, our learners, sometimes they get confused of what is it that it is this momentum. So in that number, just tick one, and then colleagues will just go to that, or maybe make two clicks, then everything that I've just said, it is going to appear, I think. So colleagues will be there that now, if we are talking of momentum, we should explain momentum as a quantity of motion that the object will be having. So that quantity of motion, it is not velocity, it can be anything, but that product, it is a quantity. And then it can only talk of motion, of momentum, if the object, it is in motion. If it is not, then there is no momentum. I think that is basically what we have as an explanation. And then in the next bullet, we are looking at the definition. And I want us to look at this definition because it was also having bearing in the test that we wrote, in fact, in the examination. Just click one, Baba. That is the definition where we are having a P, it is equaling to MV. But if we're looking at that product of the object mass and its velocity, there are two issues which are there. It is the mass and the velocity. So there are relationships that momentum at that particular case will be directly proportional to the velocity, but there must be a condition for it to be directly proportional, that the mass of that particular object, it must be constant. The other part, it is that we are looking at momentum being directly proportional to the mass, but for that, then we have to talk to the velocity also being constant. So we need to talk to those two, because it is those two that are having a bearing on that particular. But when you talk to momentum where the mass, it is increasing, the mass, it is going to be increased if on top of whatever object that we're having, you are putting in maybe another object. And this is what is really happening when we are talking to the experiment. Remember, in that experiment of momentum that we have to do, we are changing the masses, and then the velocity, then it is going to change. Now it means we have to look at this bullet very carefully. What is it that we are changing, and what variables are we talking to? Because of that, then it means from what we are having here as that part where we are having the relationships, then we have to talk to independent and dependent variables. Because immediately we are changing the mass, that mass, it is going to have a bearing on what we are going to have on the y-axis, which is going to be our momentum. So it is important that we talk to that relationship, and every time we talk of directly proportional, colleagues, on the graph, we have to present it that it should be a straight line, that it is passing through the origin. If that is not the case, then we are going to have a problem. So talking to the control variable, talking to the independent, and talking to the dependent variable, it is what is expected of us, especially when we are dealing with this particular topic, and when we are dealing with any other topic, that it is having graph, of which it can be presented as a principle or as a law. So it is important that we have to do this. Other than that, colleagues, if ever we are having a straight line graph, other than talking to the dependent and independent variable, it is already also important to can talk to what the gradient of that particular graph it is representing. So in any form, then we have to talk to what the gradient of that particular graph it will be representing. So for momentum as a definition, it means, colleagues, we cannot just say it suffices to talk to it as only a product of object mass and velocity and not go further. So we need to go further and try to put everything in perspective, so that at least going forward, then it is going to be easier for our learners to can understand. I hope what I've said here about that first bullet that define momentum it is talking about. Now the calculation part of it, it means we can do that. We are just having a mass, and then we are putting a velocity. We have to change the mass and get all those. And then in some instances, you can give them both mass and velocity and ask them to can get the momentum. And then because of that part, then it is also important to include also that momentum, it is going to be a vector quantity, and why it is a vector quantity. Now, after talking to that, then it is going to go to what is it that it is happening? Because now we are saying it is directly proportional. We are expecting if the velocity is changing, then the momentum must change. Because of that change, then it is important that we go to the next slide, which is going to talk to the change in momentum. So you cannot just in that leave it as loose as it is, and then just say momentum, change in momentum, it is momentum final minus momentum initial. We cannot just talk to that, but we have to talk to change in perspective and get what is it that we want to talk to. Because if we are looking at this, I'm saying because the velocity of the object is changing, then momentum will be changed. It means the initial value is not going to be the same as the new value that we are going to get. And because that value it is not going to be the same, it means when you go to that part where we are having change in momentum, it is equal to P final minus P initial. We have to concentrate on the P final because it is what it is has now changed. So we are looking at the change. Now, for us to get the change must be what we are adding to the initial. So whenever we are going to do the vector part of that, then we have to look at it that P final will always equal to P initial plus the change in momentum. That is the essence of this slide. So it is actually the vector sum. And then why we are putting it as a vector sum? Because in grade 11, we are talking of a resultant vector. So because momentum is a vector and then resultant to this, it is a P final, then we have to come up with the way we are presenting the vectors. We cannot just loosely put the vectors like we are not putting them as we are doing it in grade 11. We have to put everything the same as we are doing in grade 11. We cannot change the way we are teaching in grade 12 when we are in grade 11. They must be the same. So that is basically what I'm saying in this particular slide. Now, I want us to look at the change in momentum. And then I challenge you, colleagues, that in that change in momentum, it cannot just be only one scenario that it is there. And I'm going to couple this going further with what I'm going to say later. That number, let's move on. Can skip the 2 slides. Okay, Baba. Okay, now here, the first one, let's go back a bit, Baba. Back. Yeah, in this one, there is this bullet there. Describe the vector nature of momentum and draw. Next one, Baba. Yeah, and draw the vector diagram. Now, in that one, colleagues, when we go to schools, the schools that I've gone to, I've seen that the learners are drawing momentum initial and then they're drawing momentum final, but they're not combining the two. The two need to be combined. Now, it means in that we need to look at the 3 scenarios that I just outlined. Baba, let's go to them in the whole slide because I think it is going to be taking time if you go. Yeah, the first one example that we are going to look at, it is that one, colleagues, where we are having an object speeding up in the same direction. That means this one, we are having this object accelerating. So if it is accelerating, what we expect, we expect the learner to can do a calculation of momentum initial, momentum final, and then the change. Why momentum initial and momentum final? We are addressing what it was said in the very same week that they have to calculate momentum. So it means they have calculated the momentum, they have substituted into that, and now they got this. But what we have seen, it is our learners, when they present them in the books, they represent that momentum initial, they represent momentum final, and then they represent momentum initial, and then just leave it at that. The fourth part there, where it is written number 4, it is not always written. Now, I want to talk to that, and then we understand how we do it. Now, when you draw this, we have to start first drawing the initial momentum. Now we are having that initial momentum, and then what happens to it? Then there was a change that was put to it so that we end up with a bigger momentum because it is accelerating. Now that means the initial momentum, it was 10. Now that's change. It is not there, but the final, it was 30. Now, what is it that we have done to the 10? To the 10, it means we have added the 20 so that we end up with that final momentum there. That is why in this particular case, the vector diagram, it should be talking to the final, which is the resultant, which is the final, that it is going to be in the same direction in this particular case as the change. The change and the final that in the same direction, and also the initial, because everything was added and then it was positive. That is the first scenario that we are looking at. So please, colleagues, let's try to talk to this scenario as we do it with the learners. And then I want you to also look at this. I want to couple it already, because we cannot divorce this from Newton's second law, that this object now, it is accelerating in the direction in which this object it was moving initially. So that means, therefore, the momentum to be there as it is accelerating with time, which is Newton's second law now, it will be coming in, though I am coupling it already here, that with time, then that means that change in momentum or the final, it is in the same direction, because why? It is what it is happening with Newton's second law. Remember that first part, that then the body will accelerate in the direction of the net force, and the net force, it is equal into the change in momentum divided by the time, or by the time. By the time, it's a scalar quantity. So meaning that the change in momentum and the acceleration, they must be in the same direction. I hope it is clear, this example. Baba, we can go on. Right. So this is basically what I was referring to when I was speaking to this. Now, the second one, colleagues, it is for an object slowing down. Now, if your object is slowing down, that means there is acceleration in the opposite direction. And the net force, it is already also in that particular direction. So let's check what is happening. So it was the same object. Now it is moving, slowing down from 5 to 3. So the direction here, it is very important that we do the same, and then it must still talk to what we are saying. That we are having that initial, now the final, it was starting at 10, now it is now at 6. Now what is happening with the 6? Then that means then the final, it is lesser than that by 86, but it was 10 initially. So meaning that we have to subtract, and then subtracting, it means we are going lesser and lesser on the initial, because we are changing there. That is why now the change in momentum, it is going to be in the opposite direction. And then if we look at it to compare to the initial, you see that they are in opposite direction, because it still should address Newton's second law. We cannot run away from it. Next slide, Baba. Right. The third bullet that we are going to look, or the third scenario, it is what is happening when an object, it is hitting back or is bouncing off the wall, or it can be a racket or it can be whatever. Then it is the same. In this case, I didn't do it using the velocity. I go straight to the momentum, because if we're having the ball at that initial momentum, it was 6 east, and then the hidden opposite direction, now he's moving it at 10 east, then also in this particular case, we could see that now the momentum are in the same direction. But now, because the initial and the final are not there, now we have to talk to it, that part, look at the initial momentum and look at the final momentum, and then that will tell you what is it that it is happening. Now the momentum, the change in momentum and the final in this particular case, they're in the same direction, because they still have to obey Newton's second law. So basically, this bullet, we cannot just put it and do one activity and then that is enough. It is not enough, colleagues. For that bullet, I have outlined at least 3 scenarios in which we can have it, and then we can look at this and then we'll get it correct. This far, I think, Mr. Namban, we are doing well. I don't see any question, so maybe we can proceed. That colleagues, they understand that that bullet, it is not only that part, and then we just leave it as it is. Okay. Now, colleagues, this slide, it is basically what I have already incorporated, that we are going to look at Newton's second law in terms of momentum. So basically, this are what is expected in the formula. But now we go to that third bullet. The third bullet says, calculate the change in momentum when the resultant force acts on an object and its velocity. That is what is basically. Now, what is expected of us? It is this scenario number one, where we are having an increase in direction of motion. So that means it is in conjunction with that first one, where we are having an object accelerating. So in this case, you move from that one, because the learners, they do understand at that particular juncture how we did the change in acceleration or and change in the velocity. Now we go to a rocket. So stage two of the rocket, then this is basically where we can have the very same application and then we do it. So colleagues, let's take that first example and incorporate it to this second stage of rocket. Now the second one, it is going to deceleration. We apply the brakes as it is. Now this one is as it is, and in that particular slide where we are heavy. The third one, his one here, colleagues, it is where we are having the ball being kicked or a tennis racket, it is being applied. So these are the examples that we are having that are prescribed for us to can do, and then we expect you also to can do it with your learners. So incorporate each and every example in whatever way we can have it, but at least there must be something that it is taken to this slide. And then the next one, colleagues, is talking to impulse. Now, moving from the Newton's second law, we move to impulse because we just cross multiply and then we get what is it that we want in that particular case. So the change in momentum, it is going to give us all this. Now we have that definition. That impulse is a product of the net force acting on an object and the time the net force is in contact or acts on an object. Now, from the internal model research report, we'll find it that the learners were not talking to the contact time. They were just saying it is a time. Or they were taking it verbatim as it is, as in the formula, that it is a product of net force and a change in time. The time is not the change in time, it is a contact time. So because of that, then becomes a misconception that they are looking from the formula as a contact time and not, in fact, as a change in time and not as a contact time. And because of that, they were losing 2 marks. So please, colleagues, let's talk to that already, that the time there, it is a contact time and not a change in time. So we will come back to that one when we do this. Now it says there we need to do a calculation of this, and then not only on this calculations, colleagues, whenever there is a calculation, let's try by all means to also put whatever we're having as a calculation here in the form of a graph. Now that is where now we'll be having the graphs, the three scenarios of the graph, where we are going to have the momentum versus time graph, because it is going to give us that change in momentum. It is going to be there over time. Now, once we have that, then that graph can be plotted. And then we talk to the gradient, we talk to the y-intercept, we talk to area, everything that it is there to can look at what is it that we are looking. It is just a matter of drawing a graph and then talk to the graph the way it is. Now we are having some scenarios which I have seen in some of our colleagues, that we are having a velocity versus time graph, and then already colleagues are incorporating as early as this, where there is a change already in time or a change in velocity because of collision. Be alert that don't put a collision too early, because we still need it during the collisions that we are going to do during the conservation of linear momentum. So please, let's give them a way of addressing whatever we are trying to address. Let it be according to the bullets, because the bullets based on this, when you are talking momentum impulse theorem, it is all about safety consideration. And when I look at the books that I have done, I have already seen that in the safety, we are lacking in some of the aspects. That some of the colleagues are just concentrating on the airbags, and then they did not do anything about the seat belts. They didn't do anything about the arrestor beds. They didn't do anything about the crumple zones. So all the 4 scenarios, colleagues, because they're examinables, they need to be addressed. So we cannot just leave them and then say, no, the learners, if I know they know of the seat belts, then it is going to be another one. Now, talking to this bullet, colleagues, it means when you talk to it already, it is the way examination guideline it is putting it. I took this from the examination guideline that explain how the concept of impulse implies. So it means immediately it's really a concept. We need to support this explanation with a principle or with a law. So the first thing that we'll have to look at for 1 mark, those learners, they must give us the formula, the way it is going to happen, and then they give us the relationship, and then there must be something which is constant. So that means it goes back to what I said earlier about momentum, that we are having P and V, but some of that variables need to be kept constant. So the same principle it's happening here, and then from there, what momentum it is going to be constant, what happens to the net force at the time of contact, it is now becoming bigger. Now, the other thing that the learners will be doing here, it is to say that they are indirectly proportional. Colleagues, they can never ever be indirectly proportional. We are not in an English lesson. We are in a physical science lesson. They are inversely proportional. If they are say indirectly proportional, 1 mark it is also gone. And then the other thing, it is about the time. It is the contact time. It is not the change in time. It is the contact time that it is now becoming larger, or it is becoming bigger. And then as it is becoming larger and bigger, then the net force, it is going to become less. And then that will result in the person getting minor injuries because the force applied, it is not as big as it was supposed to be, but it is going to be what we are having. And then we are talking to that particular slide there. And then from there, colleagues, we need to talk to conservation of linear momentum and elastic and inelastic collision. Colleagues are doing very well with that bullet, that they are already doing the conservation of momentum, elastic and inelastic. Now, in the case of elastic and inelastic collisions, colleagues, we cannot just make them equal at the beginning. I think from last year, we have seen that if a learner did that, already we're taking away 1 mark for coming up with a conclusion, and then later they are changing that they are no more equal. So encourage your learners to do them separately. But now I've seen a trick with the colleagues. Colleagues are very creative. When we say don't write an equal sign, do them separately. Now they're putting a line instead of an equal sign in both sides, of which it's a good innovation. But now after the line or on top of the line, now they're putting it's not equal into. Now becomes another thing that I don't know now how to address it. So colleagues, they're just in a way very creative, but will accept. And then that is the last bullet that I was talking to. So colleagues, please remember again that for collision to be elastic and inelastic, we are using kinetic energy. So our learners, they are still using momentum before it is not equal into momentum after for that. And then we cannot accept that, colleagues. And then can we go to the next slide, Bob? The next slide, colleagues, it's about the ball bouncing, and then that is still on the impulse. I cited an example there, I think that should have come in, talking to the very same graphs that I was talking to. So I took this example. Now we are having this ball and then it is hitting the ground. But the point of contact, it is where, colleagues? The point of contact, it is where the time it is hitting. That is where it is, when it is hitting there. Now, we are having a force going in one direction and then it is returning. Now, to present this, colleagues, remember, at that particular time, we cannot also defeat the issue of inertia. That this ball, when going to hit that wall, it should be saying it is coming up with a particular velocity, but when it comes back, you cannot just come back without stopping. Initially, it is going to be defeated if we are not going to do that. So it is going to be a problem. So that means we have to show that that even though it is moving in the direction and then coming back with that, at some point it should be where we are having the maximum. And what is happening at that particular maximum? At that particular maximum, that is what I have put on the next slide. And then talk to it, colleagues, please. It is my plea. Let's talk to this slide. Right, this is the one. So it is the same. That now, this graphical presentation, we are having this force as it is going, but hitting the wall, where we are having that force of distortion, that is where it's going to be a change in direction. Now we need to talk to that point. We also need to talk to whatever we are having here. Now, once we are having a figure in physical sciences, colleagues, then we need to talk. Meeting will be shared on YouTube. Okay. I don't know who is that. But at that point, colleagues, we need to look at this. Now, importantly, this is going to be the net force. Now, this is the change in time, in seconds, that it is happening. So basically, this part here, it is going to talk to the area of this particular graph. Now, the area of this particular graph, hence, on the x-axis, it is already changed, put in as a change in time. It is not only time, it is a change in time. And then from this, now we are talking area under the graph. What does it imply? Now, it means because of the half, having two forces, but now one force is going up and then the other one is going to the left or whatever, to the right and left. Now we have to talk to the average force because we are having those two forces. And then that is average force multiplied by the time. Hence that half, it is very important there. What does it imply this? And then the height of this, it is just going to be whatever we are having, can be the time or whatever as a base. Now, that is why I'm talking to this base here. That even though maybe we are saying in the form, it's half base, but the base is not the time, it is the average for that we are looking at. It is going to be that one, and then the time, it is just multiplied by that. Now we end up with this. Now this part where we are having net force, it is coming from there, and then the change, it is coming from this. This is the y and the x-axis that we are addressing, and it is giving us this F net delta t. That F delta t then is a formula that we know. Then that is going to be what it is going to come up as an impulse. So it is important that we talk to this graph and any other graph that it is associated with this particular points that we are having. So please, colleagues, let's try our best to can look at this scenario and then couple this scenario with the examples that we are having and also look at last year's question paper on momentum, because it was all about this aspect and then how it was asked. And then we'll also talk to it later when we look at the internal model sport in full. Next slide, Baba. Number. The next slide is talking about a vertical projectile. Yes, this is what we have, and this is the outline that we are having. Now, worry me, it is quite a number of issues here that I've seen already, colleagues, that we need to look at. That majority of the exercises with the teacher that we have had, instead of doing the three motions that we are having, that is, a ball is thrown down, and ball is thrown up and down, coming back, and then passing that part. It is when we start, colleagues, when we start, maybe it is the way I'm doing things, of which I like it, because we are saying we are having vertical. Now, vertical means we are going to look at motion because it's a vertical motion, basically. Vertical motion of this object, which you call a projectile. Now, because it's vertical, now it means I'm already talking to the direction that I'm going to follow. I'm going to follow the direction along the y-axis. So one is going up, one it is going down. So the two motions will always be there. But now I'm having a problem with the way we put it, that it is a motion, that it is coming for a vertical object, and then we go to the projectile. But immediately we are saying to the projectile, or we are addressing the definition of a projectile, are we already showing the learners where we are heading to? Because in that definition, it says it's an object that is given the initial velocity. Now, immediately talk to that initial velocity, then we must come up with already a plan that in this, it means I'm going to have an initial velocity where an object, it is thrown. So how is it going to be thrown? It can be thrown down, it can be thrown up. That is the essence. And then from there, what is it that is going to happen? If it is not thrown, then that object, it can be released. So already the three scenarios, if I talk to the object itself, now I must also in a way try to graphically present what I mean, that it is going to be thrown up. Now I'm coming up with the direction already. My up is going to be going up positive, or it can be going up in the negative direction. So I have those arrows pointing them. Why is it important already to point that the accelerate, or in fact the velocity will be increasing? Is because at that particular point, if it is just thrown down, it means throwing down, it means thrown at a particular velocity, but it is going down. So down, I'm already taking out the misconception that when the object, it is reaching the ground, at the ground, then the velocity will be zero. Now I show them already that there must be an increase. So I don't need to go and emphasize it again and again and again, that on the ground, and fighting them that on the ground the velocity is not zero, because I did not show them already when I was doing the projectile the definition that then I have this velocity, it is given, and I throw it down, that it is going to increase and increase. Unlike when I throw it up. When I throw it up, I'll be throwing it up, but because of the gravitational force, I'm not supporting the gravitational force. I'm trying to go against the gravitational force, that at some point at the maximum, because it will come down, there will be a point where, because of inertia, it needs to come to a point where the velocity will be equal to zero. I have to talk to it, that at that particular point, immediately I throw it up, then it is going to come down. And then what is it that it is going to happen when it comes down? Then it will be coming down back to my position, or it can pass. So I need to talk to all those and then not just leave it as it is. So it is a matter of dropping it down, throwing it down, or I can throw it up, then it is going to go up and then comes down and come maybe to the position where I started, or it can go back and pass it. So those three scenarios, colleagues, we need to talk to and then try to help the learners about them. From there, colleagues, what we have seen is every time we are asking the learners to calculate the maximum height, to calculate the time reaching the maximum. But we have never seen it where we are maybe asking the learners already to can talk to the formulae the way they are, but we'll talk to it later. So everything in our case is throwing down, is throwing up, but throwing down, it's very limited. And then also the direction is very limited, but we'll look into that. So when we go to the calculation, the graphs, and prescribing the motion, then we'll look into it. But this is basically what we are going to look at, and we expect you also to look at this situation as you go down. Now I'll just put some Tatenambani as you move to the next slide. In the very same first week of projectile motion, you can go on, Baba, until the last point. This is what I was talking to. Now, here's one colleague that I was referring to, that immediately I say throw it down. Okay, it's fine, leave it here, but I'm throwing it up, but now my up is negative. So it is up. Now, immediately we say you are learners, we try to help them, that throw it up, but the learners know that it is going to go down. If we ask them to draw the trajectory of that trajectory will obviously be the same as the position time graph. It's for them just to put in the time axis and the displacement or position axis. But now I cannot just leave it there. Throwing it up already, I'm avoiding, colleagues. Immediately I go through this, I'm going to say, when I'm going to do the calculations, I must tell my learners that I'm expecting this type of graphs to be there. But with us, what we have seen colleagues is, colleagues will be doing calculations, and calculations, and they just leave them. But what we are saying is, time is not on your side, colleagues. You cannot say, now for this week, I'll be just doing, concentrating on the calculations. And then next week, I will be putting in another week in sketching the graphs. The 2 weeks that we are having, is that is week 3 and week 4. If we are looking carefully at that is where the planning is coming in. That in one, it says plot. And then in the other one, it is now saying, now what do you have to do? You have to, for the given, now interpret. That is where that describe the motion in width. So what we are saying is, in the very first week already, colleagues, whilst we are doing the calculation, already plot those calculations so that the learners know and understand the velocity time graph, the position time graph, and the acceleration time graph, so that when they are given to them, then at least we are grounded, that at least we know we have done that. We didn't rush. So by the time you are plotting already, when you are doing your calculations, try to plot the very same graphs. Then it is going to help us. That is what we are saying about these 2 slides that Nambani has done. And then we can see that now here, even though we are having the upward and the downward motion, that means this object, it is returning to the original position from where it was thrown. So important it is, when you go to the velocity time graph, they cannot just plot it the other way, the way they want. It means that's part of the area between the graph before it crosses. It must be almost the same area as above the line. Below the line and above the line, they must be the same displacement, because it's coming back to where it is. If it is not, it is going to be a criteria, obviously, when we're dealing with the graph drawing, that we have to ensure that they end at the same position, because immediately one is bigger than the other one, then it means it is not what we wanted to do that. So it is important that also we need to talk to this. Now, we are having this other part that I want us to look at, colleagues. When you talk to the area, can we use the area between the graph and the time axis? Because why? If we are looking above the line, under the graph, it is going to be cutting, in fact, touching that x-axis. But the learners will continue here, where on the negative, it is not touching the time axis. So it is going to be a wrong area. So please, let's try to use, it is going to be the area between the time axis and the graph, so that at least we try to carry our learners to the point where we want them to be, and not just leave it as it is, the way we just leave it as loose as it is. And the acceleration time graph, it depends on the direction that this learner has chosen. In this case, the learner has chosen going up as negative, hence it is starting from the negative side, reaching the maximum, and then going down, then it is going to be a positive value. So this is basically what we have. So direction and the way we are putting to the learners, it is very important that we understand what is it that we are looking at. Next slide, Baba. It is just passing that point of projection, so we can maybe skip. Okay, yeah, this one you can skip. It's the same thing. Oh, just hold it there, Baba. It's fine. Even that one is fine. Just go back a bit. Yeah, in this particular case, colleagues, we can see here the up to that point, that distance is not the same as this distance. So it means, as you draw the projection, you can see that this distance is not equal to the same distance as it is. So when they plot it on the graph also, this part should be smaller and that one should be greater. So these are the things that we are saying. We have to secure the marks for the learners. That these are the points that we are saying, take care of them as early as now, so that at least the learners, they are getting grounded. And to do that, it means we need to can put these graphs in and out, because graph presentation and graph interpretations are a problem to our learners. So we need to do these things, and then we have to, colleagues. Please, let's try our best. Next slide, Bob. So here it was just wrong. thrown up. Now here's a object that it is falling. So for you to fall, it can be at any point as it was falling or as it is being thrown. So also we need to look at this. It can be looking at it as it is now, it is just following after it was given the initial velocity which is greater than zero or whatever. So all this, but the position, what is happening when you throw it up, then it is moving from that point and then it is going to increase the position. So as it increases position, then that means also the velocity will increase in depending on where you are throwing it. If you are throwing it at zero, then it is going to be zero, cannot. So we cannot throw it, but at the same time, then it is velocity, it is zero. It is not going to be like that. So it is going to have a particular velocity, and then that is going to happen. So in this particular case, it is just that downward it was taken as positive, and then we can move at the next one, but it is just a change in direction. But it is the same thing. It is the same thing. So we talk to the reference and then we change whatever we are having. So this is the same. So in this case, we are just leaving it as it is being dropped. Now here I'm talking to it. Even though it is dropped, the displacement, it is dropped from a certain direction and going down. Now it is going to go, that displacement is changing. Now the velocity. Now, you see the relationships that we are bringing in, colleagues. We are looking at the position, how it is changing, how the velocity is changing, whereas the acceleration, it is still the same. And here now we are talking to the drop, whereas there it was just thrown down, or it was just looking at it because the velocity was not zero, then that means that object it was thrown. So all these scenarios, we are not just taking one and then saying, maybe thinking that the learners will understand everything. No, it is not about that. So all these scenarios, they must be there, colleagues. Please, it is our humble plea that we do all these things and then we get to do the things. Now, the other things, colleagues, we are not having problem. If we look at the internal models report, we are not having problems with when we are having a one object. It is easy to do it. The learners, they do it. But now when you go to two projectiles, the calculations thereof and the plotting of the graph and everything becomes a challenge. Now, colleagues, we need to talk to it that the learners, they need to put each one with its formula. We are not combining the two. They need to be treated separately. And I want to talk to only two scenarios that we are having. That is when we are having two balls, and then it is either they're going to say they're going to be giving, maybe one is going to go up and at the same time. You see the part of the same time, the other ball is dropped. One is going up and then the other one it is dropped. But in essence, I want to talk to the time. In that particular case, there is no one that comes later than the other. So that means that time there, it's not going to be a problem. And that is where we should be starting. If ever we are going to have the two, start where the time it is going to be the same. Now from there, where do we go? We move from that one, and then that's from there we move to a point where we say object A, it is now thrown up, and then 1 second or 2 seconds later, another object it is thrown downwards. So immediately we are saying that try to help our learners because they don't know now when to add the time or when to subtract the time. So in order for us to help them, ask them, okay, between object A and object B, remember object A was thrown and then 2 seconds later, object B, it is thrown or it is being dropped. Now between object A and object B, which one is having a bigger time while it is in motion? So obviously it is going to be object A. But now by how much it was having more that time? It means it is going to be by 2 seconds. So already when we say that, what is it that we are saying? We are saying now the time of object A, it is equal to some time plus the 2. Now that time that we put in, that t that we put, it is t plus 2 seconds. It means it is for ball A. Now for ball B, what is happening? Ball B, that means itself, its time will be equal to t because it is just that we make it as a reference for us to go and get the time for ball A. So ball B time it is going to be only T. And for ball B, it is going to be equal to T plus 2. Right? Now, I'm not against for the people who will be saying, no, for ball A, the time it is going to be T. To go and get the time for ball A. So ball B, time it is going. Okay. Now, for ball A, the time it is now T. Now, it means ball B, it was later. It was late. So they are putting for ball B to be T minus 2. I don't have a problem. As long as you can just clarify when you want your learners to add and go with the addition or you go for the subtraction, because our learners will have a problem. They don't know. So stick to one. This one of T plus 2 or T plus minus 2, it is the same as what we are dealing with. The 4B and the 4A, depending on the taste that we have when we are dealing with the chemistry. It is the same. Now, the two now will be doing what? They are going to change the speeds, because one it is thrown and then the other one it is dropped. Then the speed it is increasing as we drop. The ball, if we are throwing it up, we have seen that it is going to decrease. So basically, the decrease, it is because immediately looking at that, then it is going to be about the change in velocity. And once we have that change in velocity, it is not a velocity that it is changing because of the external force. That velocity is changing because of the gravitational force. Then it is important that at that particular point we say that acceleration, because we are having a change in velocity, with time, which is acceleration, it is due to gravity and not any other object, in fact any other velocity which is there. So here, colleagues, the acceleration, it is going to be gravitational force, gravitational acceleration. But for the hot air balloon, if we are looking at it, the hot air balloon, they will be saying it is moving at a constant speed or a constant velocity, meaning that even if we are looking at the displacement, that displacement, we still have to put what we have as acceleration, but the acceleration for the hot air balloon, because it's still rising up. Rising up, it is because of the expansion in the gas. It is an external force. Now, the net force and the acceleration there, they are not due to gravity, but they are external. So the acceleration there, because it's moving at a constant velocity, then it is going to be equal to 0. So if colleagues can address those two, then they can calculate the distance between the two objects as it is moving up, when it is moving down, but at least colleagues will have that. So please, colleagues, let's look at the two scenarios before we even go to organic chemistry, like we are having. I hope we are getting there, number. Thank you, colleagues, for agreeing with what I'm saying. I hope colleagues will address them. Can you go quickly to the bouncing balls and then we look at them? Even the next one, but just one. Thank you. Until there. Colleagues, it is the same with the bouncing ball. And that number has put already that one. I wanted to address it. It's fine. I'll address the whole slide. Colleagues, it is the same. For bouncing ball, we still have to sketch velocity, time graph, time acceleration, displacement time. Now it is all about this. They need to sketch them. Sketching them, talk to why are they not going to the same height every time they are doing this. The peaks are becoming lower and lower and lower. Talk to it, colleagues. It was a question that we need to address. Now, there are quite a number of things that is happening for bouncing balls. As we are learners, when they hit the ground, there is a sound being produced. There is a friction with the wall. So all those, because of that point, then there will be a loss of energy in the form of sound or in the form of heat. That is why then we are going to have this. And then, even though here we are talking to bouncing balls as if the only force acting it is equaling to, in fact, only force acting is gravitational, but when hitting the ground, it is making some changes. We understand that, no problem with that. But now, when we go further, we need to talk to these points where there is contact. Is the time of contact indicated or is it not? If it is not indicated, now there is no point. We can just leave it and take it that then we don't have to show it. But when they say there is a contact time with the ground for this, then it is important that when we go to the velocity time graph, we also indicate that time. Hence, on this graph for velocity time, I have indicated that we still need to do that contact time. But if it is not there, colleagues, we don't need to show it. And then the other thing, colleagues, about this, talk to the part that when hitting the ground, it was going down. But now it changes the direction. Now it goes up, and then at some point it reaches zero. It was up now. So the direction before it comes to zero, it was up, and then it was having a certain velocity which was greater than zero, because we know for an upward, then ultimately it is coming to zero. So our learners need to talk to that first part. And then when reaching that ground, now it is going down, like when it was dropped. So these 2 points here, they must talk to the same. And then also try, even though here it is not clear, that the area between the two, they must try to be almost the same, colleagues. And then from there, they go down and down and down. So please, colleagues, these velocity time graphs, we need to talk to them and address our learners to draw them correctly. And the only way they do it correctly, it is when we are giving them the exercises. The other graph that we could have done here, it was not for them being dropped, but for it being thrown. So thrown, it is coming from the earlier parts that they need to show us that first part of the velocity, that when it is thrown, it is having a certain velocity. But now we go to the next part, and then this is going to address what I want to address. That when you go to these lines, they must be parallel, because they are subjected to gravitational force. And the gravitational force, it is equaling to W, which is mg. So the g which we have is gravitational and it is constant, it is equaling to 9.8. Hence, when we draw the acceleration time graph, it is just one straight line, colleagues, right? Because it is coming from the velocity time. Now, this other part where we are having the arrows pointing up and down there, colleagues, that one, can we avoid it even for our learners? I know at those points where we are having some sparks there, it was when it was in contact, but it is defeating what we are teaching the learners. I know in some books it is there, but we expect them to draw an acceleration time graph because it is a projectile, and then we are saying the only force acting, it is a gravitational force. Then we are saying the acceleration at that particular point, it must also be a straight line. So these other two graphs on the right, being it positive or being it negative, colleagues, we don't need it. Please, let's try by all means to avoid them. I hope it is clear, colleagues, what I have said there. Let's move on to the number. All right, thank you, Bob. Now, one of the bullets that are there in week 1 of vertical projectile, which is week number 3, it is saying give the equation for position versus time. Now, who should give? It means the learners, they must give us that particular equation and the velocity versus time for the graph of one-dimension projectile motion. Now, for the position time graph, colleagues, we need to come up with a general formula. If the position time graph, now we must anticipate already, because from the previous slide, we have seen the way the position time it was shaped. It was a parabola. So it means the equation that we are going to develop, or the learners need to develop, it should still also show the position time graph in the form of a parabola. Now, it is important that we know where do we start for our learners who can come up with that correct equation. So we start with that formula. delta y equaling to V initial delta t plus half G delta t squared. Because we're having the t squared and it is on the x-axis, it is already showing the form of we have to go to the ax squared plus bx plus c. That is the essence of what we are having. Now, what is it that we are having? I try to explain how we arrived to the last formula there. Where we are saying now from there, we look at the change sy final minus y initial. That other part, I started with the half gt squared plus v initial delta t. So it is just rearranging that formula. And then I take the y initial to the other side. That is line number 3. Now I substituted. What is it that we are going to substitute? It means my half multiplied by 9.8. It is the G, it is there, they know. Now it is going to be giving us, if that is going to give us negative 4,9. That negative 4,9, now it is going to be equaling to your a in the parabola. And then the t squared, it is going to be on the x-axis, we are having a t. So it is going to be the change in time. And then the b part, because here we are having v initial, my b part then is going to be the initial velocity. Meaning what? If an object is thrown with a particular velocity, then the learners, they must put in that value of the v initial at that particular point, right? Second part, it is the y initial. What is the y initial? It is where the graph is touching the x-axis, the y-axis. So meaning that y initial, it is going to be equaling to the height from where the ball was projected. And why is this important that we look also at this? Is because remember, there are points when we are saying calculate the motion or the position of the ball in 3 seconds if it was thrown from maybe 5 meters above the ground. So that means at any given time, then these learners, they can be able to can use this formula and get that. They did not need to redo the calculation, substitution, and everything. So from that formula, they can still work it direct because it is going to be about 2-3 marks. So they must know that. And then I've just changed the direction in the next slides. Then we are going to do that. Where again is this applicable? It is applicable when we are dealing with the vertical projectile where we are having a balloon and the object. Now, as the balloon is reaching the maximum height, they can calculate the time at which the balloon is reaching the maximum height, and substitute that part to look at where the camera that was falling, it is coming, it will be at that particular point. Now, after getting that, now to calculate the distance between the two, now it is a matter of one it was going up, one it was going down. Now they add the two so that at least they can get the distance between the two where they are. So basically, this formula is a very helpful formula that we cannot even not address it because the learners are expected, colleagues, to can also get this formula and give us that formula. So it is just something that we need to look at it. But that is for the position time. There is one for the acceleration time that we also need. In fact, for the velocity time that we also need to look at. Next slide, Ba. Father Nambani. So the next one, colleagues, it is looking at the velocity time. So with the velocity time graph, which formula are we using? We are using just the first one, Baba. Previous slide. The previous one. Mm-mm. Yeah, this one, Baba. So this one, colleagues, is talking to velocity time graph. Now, what is it that we know? It's a straight line. So it must be next one, Baba. Okay, someone split. Okay, Baba. Next one. For velocity time. On your side, maybe it's appearing. On my side, it's still talking to position time. I want the one talking to velocity time. Yeah, this one. Thank you, Ba. So this one, yeah, it has moved. Okay, but colleagues will get it. That it is talking to velocity time. So for velocity time, we are talking to V final equaling to V initial plus G delta T. So it's a straight line. Velocity time graph, like we have seen in the previous slides, it is just a straight line graph. So it must have the form y equaling to W, y equaling to mx plus c. So we need to rearrange this, colleagues, that now we are starting with V final, but we want the G as a gradient because already we talked to it when we are talking to the velocity time graph that the gradient of that particular graph, it is actually G, and then we rearrange this and then we talk to it. So what we are saying is, therefore, on the y-axis, then it is going to be non oh, how is it now? Okay. It got contact. It's in. So I'm saying a typical multiple choice question that was asked, it was to say, what is the gradient of the velocity time graph? So from this graph, from this equation, we could see that your m, which is the gradient, it is actually the g, and then the initial velocity, it is actually where the graph should cut the y-axis. So it's important that when they draw, they don't miss this point that the initial velocity, it is where the where the graph is going to cut the y-axis. So there are 2 points here that are already marks for our learners that the starting point or the initial velocity is where it is cutting the y-axis, and then the gradient is equal to 9.8, which is going to be what we are having there. I think it's covered. Let's move on. Next slide. The next slide, it is, yeah, this one, colleagues, for the given. It's for the given. That means they are given these graphs. So we have to do these calculations. Here we have to look at how this was one graph that is just ordinarily, but here it is for the bound symbol. So they can be given this. But when they're given this, in both cases, what is it that is this? The solution is to determine the variables are either used for calculation for using the equations of motion. If it is calculation, now we can use that for any of this given, or we can determine the area between the graph and the time axis. We can see there, colleagues, I avoided by all means, we can say under, and then determine the gradient. So basically, when they're having this, these are the points that we need to look at. And we also look to reading from the graph. What is it for us to do this calculation? These learners, they must be able to can read from the graph so that they can do those calculations. If they are not able to do those calculations, then it is going to be very difficult for them to do those calculations. So reading from the graph or interpreting the graph is very key for us to can do that. And then they can use the mathematical definitions also for certain variables. You see here for the gradient, if we are saying speed of the velocity as a rate of change, immediately we are talking of the rate of change of displacement. If we are to do the speed or the velocity, this is coming from what we are saying as a mathematical relationship, that we are having the speed as a rate of change. Now we have to talk to the rate that it is dividing by time, and what is it? Now it is a change in position of which it is going to give us this. So whatever it is given, then you can look into this. And this is basically as we outline and how we should approach the parts that we are having for the ATP that number. until week number 4 of the which is going to be paper 1. Now we move to the next part, and then colleagues shouldn't maybe take me for wrong, please. Can you go quickly to that one, and then we'll address some few issues, and then we go. Next slide. Colleagues, the next slide, we try to give you the rush analysis of paper 1. And if we look at question number 1, which is multiple choice questions, colleagues, it was operating at 41%. So immediately it is coming to that, it is telling us that our learners are not doing well with the multiple choice questions. So the other questions which are read are question 3, question 4, and the rest. So we are not going to go to those questions. We are going to concentrate from 1 up to 4, and then I'm going to be selective. I'm not going to do all of them. But when you go to question of multiple choice and where the problems were, let's start first with where the problems were. Let's go to it in that number, where the problems with these questions were. Next slide, it is talking to the definitions. First one, it was definitions. Colleagues, remember when we were saying we are having these struggling learners which are progressed, they're struggling, they're doing it. Our weapon was to say we have to give them some chance to can say definitions, they must be correct. But when you look at how the definitions were, then you'll realize that we are still struggling to get the total marks on the definitions. So we cannot just leave it there. Our learners are not getting the definitions correct, all of them. So for each question, that is a definition. For us to have secured the 2 marks, we have to ensure that we assess the definitions. We assess the multiple choice questions, colleagues. We cannot just wait for the formal assessment for the learners to be assessed only on multiple choice. So in between, colleagues, it's our play. Let's address the issue of also multiple choice questions. Give them 5 informal, and then there will be the pet topic. And once you do the multiple choice questions, colleagues, we are saying do the multiple choice question. Don't give the answers to the learners, but advise them why that question it is not correct, and how we advise them that that question is that answer is not correct by giving them the very same answer. Give them so that we give the scenario and check if that it is true or not. Then the learners will be able to can develop it, how we arrive at the correct multiple choice. And already, colleagues, in some it is just a principle. Now, as a principle or a law, now we can safely say very obviously 2 will be very wrong. Then they can eliminate the 2. But the remaining 2, now the principle, they must be able to can go into that principle and check which words or a phrase it is going to be wrong for them to can make an informed decision about what is it that it is not correct there. The big elephant in the room, it is explanation questions. Colleagues, explanation questions, even though they are level 3 questions or level 4 questions, but our learners, they still need to get some marks there because the definitions, they are not getting the marks full as we want them. In multiple choice, they are not getting them. Multiple choice will be having also some which are level 3, some which are level 4. But if we look at the high order questions, they just need an understanding. There will be some marks that these learners will get, even though it's a level 3 question. So all of our explanation questions, colleagues, let's emphasize to the learners that they are based on the explanation that needs either a principle or a formula. So in the formula, immediately they write a formula and the relationship or end the relationship, then they can secure at least 1 or 2 marks. The other thing where our learners are losing the marks, it is where they have to make a choice of increase, decrease. Now, we cannot say it is an increase or a decrease without reasoning it out. Why are you saying it's an increase or a decrease? Now, for you to do that, it means you still need some steps, which is basically the explanation step that we are doing until you reach that particular point where we are saying it is going to increase or it is going to remain the same. So the explanations and that decrease increase, which is 3 marks, 4 marks, it still needs the principles to be there, and then we need to emphasize them in the form either mathematical relationship or as a principle in weights. Graphing drawing and graph interpretation, I think that one talks to itself. Now, why are the learners failing to address this? Now it comes back to us that our learners are not doing number 3 and number 4 because of the conceptual understanding. So the first part that I was trying to do on the vertical projectile and momentum, it was to develop, sorry, that person, I don't know who he is. But the number, that person. Okay. The previous slide, Bob, before, and then I'll go. So the conceptual understanding, colleagues, it is for us to talk to you about it, that the conceptual understanding, it is on us, colleagues. We have to make sure that learners understand what is it that they're dealing with. So it is our baby that we need to do it. So we need to do more on them in the explanation of concepts. Now, let's go to this slide, colleagues. This is Newton's second law. I just want to talk to question number 1. Question number 1 was a definition of Newton's second law. Now, we can see it is 89% of the learners that are getting it correct. So what happens to the 11% that we are having? So we are losing them. And this question, it is worrying because it was asked 3 times in grade 11. That is in the March test, in the June, and then in the final examination. So it is 3 times there. In grade 12, it was asked 3 times. It was in the March test, June exam, in the trial, and also in the final examination. So meaning that even though we take that the learners are getting it correct, they are not. And then it was asked a lot of times, it's still 89% that it is getting right. So that means we still need to do that as Newton's second law and get the learners to understand what is it that it is a problem with that question. So the problem was incomplete definition and incorrect facing of this. Our learners are still starting with the formula. F net is directly proportional to the mass and and directly proportional to the acceleration. So they were just getting 1 mark. So it is a concern for us to have a look at this. Now, this other question, which is 2.3, it is basically grade 11 work. So basically, teachers who are teaching grade 11, please help us to can understand the resolution of vectors. Resolution of vectors, we need it because even in work, energy, and power, we are still going to need it. We need it when we do the calculations for for the friction on an incline. We still need resolution of vectors. So if our learners cannot get it right, colleagues, then it is going to be a problem. Now, the next question, Bob. Let's move. It's fine. Next slide, Bob. The next slide, it is what we're thinking. It was when we say it is the conceptual understanding. It was asking about what is happening with Newton's second law. As we can see there, the net force acting on an object on a horizontal surface is always. Now, once it is said it is always, then it means it is a law because it is something that it is there. It's a principle which is not there. So we are having a net force, and then it is an object that is having a mass. Now, it means from there, colleagues, we should be saying to our learners, we are having 3 variables that we are talking to it, and then here it is talking to acceleration, acceleration, acceleration. So already it is talking to Newton's second law. What is the relationship between net force and the acceleration? And the point of departure from Newton's second law, it is the acceleration is in the direction of the net force. If the acceleration is in the direction of the net force, then it means if you go forward backwards, then the net force it is in the direction of the acceleration. But our learners couldn't get it. And hence, we are saying the conceptual understanding, they don't understand the concepts. It's for us to make it a point that they understand what is it that it is happening. So this first question, it was 1.1 on multiple choice. Our learners didn't get it right. So it's a problem that we are having. So we need to look at it also, colleagues. What is it that it is happening? The next slide back. It is talking to what I was referring to. Thank you. So if you look at this, especially this part here, in 2.3, we can see it was momentum draw free body diagrams. Free body diagrams, colleagues, Leone, they are not getting 100%. This is simple free body diagram, the 4 marks that you could get, but 92% of our learners are getting it right, and then the rest are not. So let's try, colleagues, to look at the free body diagrams again. So change this. This force was being pulled. You change this now. What is going to happen when it was pushing down that? So those are the things that are there. And then we do the same calculation with them so that at least we get whatever we want to get. But now if you look at 2.3, the horizontal component of the force is now 15. Now it's talking to this. Immediately it's talking to that component. It is there. That is resolution of vectors. Then that's what I'm saying. Now for our learners not to get these 2 marks for the theta, it's still a mystery to us that they are still operating at 34%. It is a mystery to me that it is only 48% of the learners who got it right. 52 couldn't get. And this is grade 11 work. It's not on an incline, just on horizontal. They should be getting it. So we have to talk to this theta. It is in relation to which component? It is to the component horizontal. And then we're having that one as a force diagram applied to the horizontal. It's a hypotenuse. Which trigonometric function it is there. It was a cos that they should have used. But our learners were using what? They were using a sine. Now, is it a problem of us not giving them enough on this, or it is the learners themselves that they're becoming stubborn? That anything which is horizontal, if you are having this horizontal now from the incline and then from the horizontal, it is the same. It is going to be sine. That is why they are putting sine, or it is just a matter of front. I'm not sure, colleagues. Are we doing enough emphasis on the horizontal, or are we doing only the incline because we feel it is difficult? I am not so sure. Now, the next one, it is the coefficient of static friction. But they are saying this, it is stationary. So our learners, the formula, first thing, where we are saying at least formula it is 1 mark, they will get it. They didn't get it because they are not writing what is it that it is there in the formula. So it was a problem. So colleagues, let's try to look at everything that it is going to happen there. Every time, colleagues, when you go to number 4, how will the friction acting on the be affected? Friction, it is going to be affected either by 2 things. What is going to change as a normal? Friction, it is directly proportional to the normal. Being it static, being it kinetic, it is the normal. So this question, basically, when you change that theta there, it is talking to the normal. And colleagues, normal force, it is always abnormal. Once you change something, then Leona is going to change abnormal. You go to the incline, it's still the same surface, it is acting this way. You change the angle, it is going to be this way. So please change it. Normal force, it will always be normal. It will behave normal. If you change me from hot to cold, I will behave the way you want me to change. So the normal will also change. It cannot be the same. So it's important that we talk to the normal under each and every circumstances. Talk to the normal when we're dealing with friction. It is affecting everything in that particular case. Now, the next slide, Bob, we can just look at it. That it is talking to what it is happening there, and colleagues cannot ignore talking to that graph. They cannot, because especially go to the maximum, we can still apply it, but going to the maximum, it is very key. So we need to look into this. And then the next slide, Bob. Is it me, Tatena Money, or it's you? Okay, maybe it is on my side. I'm slow. Okay, there. Yeah, it's only then that it is appearing. So it is talking to what we are looking at, that part of trigonometrical ratios. And then the common mistake, it is the direction of the vectors, colleagues. All these two, the two really, for us to be having 44 and 48, it is trigonometrical ratios, which we think we should be getting, and then incorrect direction of the vertical component of that force, really also it is not really what it is. And then the omission of the maximum or the static on the formula, they were losing marks out of that. That is why we were at 44. And then what we are saying when teaching 11, take note of all these aspects. What is it that is on the Y? What is it that is on the X to the direct the vectors, because it is starting from there. Now, 2.4 colleagues was poorly answered. Most of the candidates, they couldn't relate the normal to this. So we have to calculate normal on the horizontal, on an incline, when it's pushed or when it's pulled. So normal will always act haphazard in an ordinary way when we are putting it in a particular situation, then it is going to go there. Next one up. It's a multiple choice question number 2, this 1.2, and then it is go to the next topic, which I want colleagues to look at. What the examiners now are looking at. Why is it so important that when we deal with the gaps, we deal them one and every one and we combine to go to the head. So it's a multiple choice question on hot air balloon. Maybe I should proceed because to my side, it is a bit slow. I don't know. So we're having a hot air balloon and a stone that it is been dropped from the hot air balloon. Now they are giving the graphs there of velocity of the balloon and the stone. So because it is the velocities, colleagues, we need to look at the plotting of that. And that multiple choice question, colleagues, I am appealing to you that when you go to two objects, especially on the hot air balloon, recall this from your archives, this multiple choice question from your archives, so that at least we address it. Did you move the slide that now and it's not coming? Mr. Nambane? The number. No, it's not. But it is what I was referring to. I don't know what is happening. Yeah, that is coming. Yeah. So I want colleagues to look at this because it's talking to two objects. It's a multiple choice question. So if we look at what is happening here, when we say a ball is dropped, small stone is dropped. Now they need to talk to this and have the learners who can understand in trying to be the conceptual understanding, because multiple choice questions is one of the tools that we want to use to eliminate the misconceptions. So starting point, they are both moving at the same point. They're moving initially at the same velocity. But with the stone, the velocity is going to increase, but it is not only in one direction, because it is going to go up and then go down. That is where the projectile it is coming in for the stone. Hence, it goes back to what we're saying when we introduce the graphs, that we need to talk to that. So basically, because it's not going to come down, it means now already number A, it is going to be wrong, right? That is on the stone part. And if you go back to number C, you see the velocity of the balloon and the velocity of the stone, they are not starting at the same point. So number C will be wrong. We go to this one. This one, the velocity of the balloon is constant. The velocity of the stone, it is starting somewhere. So this one, it cannot also be wrong, even though it is going back to it. So if we're looking at this one, the balloon is still going up correctly. So the stone is starting with the balloon and then it is reaching the maximum height and then continue. So the correct answer here, it was B. I didn't guess it. I went through each and every one and tried to explain why each and every one, it is not correct. And that is what we are saying our colleagues, they need to do it for our learners so that at least we secure the marks on the multiple choice. So training them and giving them questions will help us to make them understand what is it that we want them to do. I hope this is the approach when you go to that part of the multiple choice questions. Vertical projectile colleagues in general, after the multiple choice, in general, the performance, how it was. This is the performance, and then we can see your learners are still doing very good, and it is my learners also who are doing this. Now, the definition, which is 3.1, the same as in Newton's second law. Remember, it was 1989. Now here it is 88. So we are still not getting where we want to get with that question, especially with the multiple choice question. So it says to us, colleagues, let's try and ensure that the definitions, because we want every learner in each question to get that total of the multiple choice, because it's a point that we want. So please, colleagues, let the definitions, let's make it that the correctness and the completeness of those definitions are being carried out, and what we have. Now, if we go to the next one, that one is the question itself, and I'll just go through it quickly. There are some few points that I want us to look at. Question number 3, it is this one: a ball is projected vertically up. Now, you see now this, what is happening from a 5 meters high building, there it is. Now define free fall. That is where we get in the 88% instead of the 100. And free fall, it is a 2 or a 0. So they miss one weight because of incomplete or maybe a wrong thing or whatever. It is 0. So they're losing marks, but we need to look into it. Now, this one, using equations of motion only, calculate the value of P. Now, the P, it is on the time axis, colleagues. That means the 0, the learners need to address it. When is the magnitude of the velocity 0? It means it is at the maximum point when the ball, it was initially projected up. So we need to look at what is it that is happening. Yeah. At time 0, what was the initial velocity? The initial velocity was 15. So these two, they need to, that is the interpretation that we say they should be having. And then from there, they were to calculate Q for 3 marks. So these 8 marks, colleagues, had our learners got it right, which is very easy to get, because P is the maximum velocity when the time it was this. So it was simple formula in each. It was formula, substitution, answer. Formula, substitution, answer. And then that 8 marks, to me, all our learners should have got that, but there were so many gaps that ultimately we go to for that 3.2, we got 63, and then for 3.3, we got 54%. So I'm not sure where lies the problem. So we are dealing with this and we are finishing it up, colleagues. Before we even go further, get these velocities and then draw this as we proceed, please. It is my plea. Next one, Tate number. Now the ball bounces to a maximum height 3 after it strikes the ground. Now, is the collision with the ground elastic or inelastic? Explain the answer without use of a calculation. So basically, 1 mark it was for saying it is going to be an inelastic. Why is it inelastic? Is because some of the energy that is lost for 2 marks in the form of heat, in the form of sound. That 3 marks also, I think, colleagues, the learners should got it, because it is coming from bouncing. Why they're not reaching the same height every time? We have to do that while we are teaching. The set story is this one. Sketch the velocity versus time graph of the ball from the time it was projected until the maximum height after the bounce, the maximum height, colleagues. And then it is saying there, indicate this, the initial velocity, it was given to them as 15. time p and velocity, numerical values. Our learners were still writing this q and p, whereas it didn't need this. So it is our plea, colleague. Let's make our learners read what it is that they have to read, and then what it is not that they have to read. That number is passed. Time is not on our side. We'll make this presentation available to the colleagues in some other issues which are there. Skip it again, this one. We talked to it already. Next one, Baba. Next one. I want colleagues to look at this one also. That is coming from momentum. How our learners were treated. You see now, the momentum, it is not only P equaling to V, but now V mass is changing, of which it was what we were addressing there. So this slide just went a bit lower. I think it should have been up when we are dealing with momentum. But this is basically what we are having, that emphasizing that momentum, it is not only directly proportional to the velocity, but also momentum is directly proportional to the mass, because the masses are changing. So what happens? But in this case, the same momentum, it is the same. So what is going to be the relationship between the P and the Q? So it is important that we also compare the two, and then we go. Okay, Baba. I want you to go to question. Skip 2 slides, Baba. Skip. Yeah, this question, the previous one. Yeah, this question, colleagues. I hope you haven't given your learners this question without explaining it. For those who have given, because I've seen some have given. Colleagues, please talk to this question. If you look at the scenario, take it further, colleagues. Don't just leave it as it is. That we are having initial velocity, we are having final velocity. Already here, go back to the presentation of that bullet that we didn't do well, of the vector nature, and draw the change in momentum for this. And then from there, colleagues, we go here. What is it that it is presented? In this, it is a contact time. Now, you see, it's a contact time. And then they're telling the learners that that contact time, it is a change in T. What is this on the other side? It is the final momentum. So this value is a final momentum. But for it to be a final, then there must be something happening here, which is going to be a change. So our learners, they need to understand this. So graph interpretation, colleagues, our learners are not going to get it right unless we explain to them what is it that it is here. This 0,3, it is not time at 0,3. It's not the time at 0.1 that we are having this value, but the contact time, the change, as this was, and the contact time, it was this, and the contact time, it was this. So they have to read through here and understand. It's a weird question, but we need to explain to them what it is happening. So I'm appealing to colleagues to go through this and explain how these are related before they come up to the memorandum and give the answers to the learners, because there is a lot that is happening here. And then this ball, what is it that is happening about the change in this in momentum? Because the question, as it is coming, it is talking to quite a number of things that we are having, but we are not getting there. So I want us to look at this question, colleagues, and then I'm going to give you the solution to it, but really, we need to look at it differently than this question. It's not just a bet and then this is the time. It is a contact time. And then it goes back to that graph where we're having a triangle, that it is sticking to this, that contact time. So this question need to be treated fairly. It can help us to do whatever we have. Colleagues, let's go to next topic, which is going to be a part of chemistry because we are going to end here. That number, skip, yeah, skip this one. I want us to go to chemistry quick. Yeah, that multiple choice question, Baba, first. The previous slide, yeah. And this was a question on multiple choice questions for chemistry. Yeah, colleagues, the question, it might look easy. Which one of the following is the name of functional group of propan 1-ol? Yes, the answer is D. But how do we arrive at this? We want to say to you, colleagues, we are going to deal with this later for those who didn't start with chemistry, that we let our learners know the name and the structural formula of the functional groups as it is here. So they have to know where is formyl, where is this, and where is carboxyl with the carboxylic acid. All this, they need to know them. And then ensure that the names of the functional group prescribed in grade 12 the learners are able to identify them with the homologous series. So this is very key to us, and they draw the structures so that at least the question, whatever way it will come, then it can change. So it is the same approach that we want you to look at. What is going to happen here? So the formula and everything, please, colleagues, let's try. Let's move on to the next slide, Bob, because we are going to be a bit late. I'm rushing. I don't want to keep colleagues long. It's Valentine. I want you to go to that table, Bob. Yeah, colleagues, on the table. This is what is happening in the table. It's normal question, but colleagues, we are not gonna say we end up only if we're looking at maybe molecule A, that we go to answer the question about molecule A as it is as in the question paper. For that question in the question paper, molecule A, it was saying the IUPAC name of molecule A. Now they are given the structure of molecule A. What we want you to look at is ask all the other possibilities about molecule A. There is a chain length that can be increased. There is also maybe not, a functional isomer that can be asked out of that question. You can ask them to write a condensed formula. You can write everything, colleagues, in each and every one. If they ask you the name here, or if they give you the name like they did, go and try to look at. In one question, there was a question about structural formula. There is condensed. There is also a molecular formula. All these, colleagues, try to ask as much as possible. Ask the homologous series. Ask anything about the table. Outsource them so that our learners, they know that they cannot just be sure of whatever you're going to ask. Ask them anything about this table. That is one thing that we want to say about this. They have done well with the questions the way they are, but we need to them to get in that total maximum and not only at 70%. That is what we are saying here. So answering that question, those questions is not enough, colleagues, that we are having. That is number. Answering these questions is not going to good, it's fine. Go to that light. The questions as they are, we cannot just end here. That is basically what we are saying. We need to go further than what these questions are having. If we apply them, then maybe put in any other questions. If it is talking about A, ask them for all and not only the three. Ask for all 8 of them. If there are 7, ask about them. And the same questions, but on different homologous series, isomers, everything that it is here, but for each and every one. That is what we are saying, so that at least we beef up our content understanding and the concepts that our learners will be having. Okay, now, we try to give a lot about what is it that we want to say to our learners, because even for that structure A, which was there, they didn't get it right, that structure A. So in the presentation, if you go to the next slide, that number, because that's where most of the problems were. The homologous series, there were not so many challenges, but with that one, there was a problem. So what we did, we outlined some few steps that we want our colleagues to look at it when they're dealing with these learners. So for that structure, we are saying for numbering, they have to start from the side closest to the functional group. So if you look at that functional group, for that, it is a carbonyl, which is, it's a ketone for that one. So from there, they have to say it is at carbon number 2. Now, that means when they go to the name itself, because it's a ketone, already they must get to know that the suffix it is going to be own. And then also what it is happening, because they've seen when they number the carbons, the longest possible chain, there was something which was not there on the numbers at carbon number 3, which is going to be a branch. So because of that branch, they need to look at that branch and how many carbons are there. If it is 1 carbon, now it is obvious 1 carbon we associated with what we are saying. When people are first hitting you, the first person that you are calling, it is your mother, me. So it is it's a myth. So going to the earth and everything, it is not going to help us. We need to look at how these carbons are coming in. And then from there, we go to the parent. How many are there? And then ultimately we arrive at that one. So number A, it was a bit easy for them to can get, but also look at the numbers, the hyphens and the suffix. So to do all the steps that we have outlined here, it was within 3 marks for this question. So that was the 3 marks, which we thought it was easy, but unfortunately it was not. And then because of that, now we are outlining to the colleagues how maybe if we follow this, and then are we able to can get to it, that we are going to get the correct answer. So it was number 1. So the same goes with number 2. Go to number 2, Nambani, it is all about B. With number B, it is the same. But now, if we look at number B, then your chlorines, if you look at them, they are both at carbon number 2. If you are starting from one side and on the other side. So we have to identify all where you are having your chlorines and your other substituents and try to develop the numbers that at methyl it is at carbon number 2, so it is 2, and chlorine is already somewhere in number 5. We add all those numbers where we are having. So wherever we are having these numbers, it is 6. We add and then we end up to 11, and all those 11 plus 2, 2, it is 15, and then we end up. So moving from the left and moving from the right, we add the numbers, and then after we get these numbers, now they are going to indicate to you which one is the smallest, and the one which is the smallest, we are starting from that side to can go to the correct numbering of all this, and then the prefixes that you are going to have on the prefix, it is going to be on the numbers as they are. Methyl is the group number 2, and then also at numbers 5, we are having a methyl. So that means we are going to have 2.5. And please, it's a comma and not a full stop, colleagues, or a semicolon. So our letters are missing this very easy. So we need to correct them. What about the chlorines? The chlorines are at carbon number 2 and at carbon number 6. So we can see there, those numbers, we are starting there, and then we just put them where they are. These numbers, where are these substituents are, and then from there we look at Therefore, what is the functional group here? The functional group is a single bond, single bond. Now, because of that, it's an alkane, and then the suffix, it is going to be an alkane. So from there, we come up with the correct name, and then we do everything correct, and then the 3 marks, we are secured on it. So please, colleagues, let's try to help our learners to get all these full marks. And remember, we are having these learners which are not very good in mathematics, even though physical science is done in mathematics, but mathematics is a nightmare. So these are some of the marks where we are thinking that these 3 marks loosely, they are part of what we can achieve as we move forward. Next slide, Bob. The next slide, it is also there's almost the same. It is G. So we also start from the same. It is the same process that we are putting, starting from the closest to the functional group, which is carbon number 2. Now the suffix there, it is ENE. And now we go and check what is it at carbon number 3 we are having ethyl. But if we look at it here, the ethyl it is at carbon number 2, the meth it is at carbon number 3. Now, what is happening here? They are at different points. Now we have to give what? A preference to what? The alphabetical order. Colleagues, those minor things are the ones that are costing us what it is that it is happening. Even though it is happening 2 and 3 here, we are not going to go to the previous one and say, but 2 is smaller than 3, and then we go in there. No. Here it is all about the alphabetical order because they are not the same. Okay, we are not having the same way they're having at the same position. So this adding of the numbers is not working here and comparing the two. Here it is pure alphabetical order that we are looking at. Next slide, Bob. Okay, now these are just notes that we need us to look at that will also check that even though we are looking at the longest possible chain, then it must include the functional group. Now emphasize how to number the carbons, chain in alkanes, alkynes, and in the ketones, starting from the side closest to the functional group. For positional isomers, position of the functional group must be at different carbons, cannot just be at one, because we want to change the position. So it should be changing the position, but with that one, it's no problem. Besides hydrocarbons, haloalkane and esters, after identifying the parent name as built, it is important to include an AN in that. Why? Is because all other than besides this, that means you are looking at carboxylic acids, your alcohols, everything that is containing an oxygen, there must be a AN that is attached to the parentane, which is the number of carbons. So it is important that we also put that. So we have to encourage our learners to draw structural formula so that they can easily identify the functional group to help them to get to the answer. So all these, colleagues, is what we are putting to you and saying, as we are going to treat organic chemistry, for those who are still going to do it, or for those who have done it already, go and just check as to whether we did address what we wanted to address and what is expected of us to address. So that is basically on that one. But can you move to the next slide, Ba? Right, colleagues. It is all about reactions. Now, I'm having this slide, colleagues, about the reaction, and I've divided the reactions the way it is. I know it is in one document that we are having. So, colleagues, if we can just cut this and talk to, when you talk to the alkanes, talk to these 3 and not in the whole document. Just give it to your learners and that they paste it and then they talk to this. And colleagues, this is a reaction, I guess. And I want to look at this oxidation or combustion reaction. It's a reaction of the alkanes, which is fair. What we usually do, we just give it and we calculate. But what happened last year, Tatenamban? Can you go to that one? That slide. Because it's a reaction. Atoms, they don't just react haphazardly. They take this compound E, it's a hydrocarbon. They react it with oxygen according to that. But the question, they know that there will be gases that are formed, which is going to be carbon and a water. So they didn't ask anything on the reaction itself, even though it's a reaction. They went out and asked about stoichiometrical calculations. So what is the message that the examiners are putting to us? It's in a reaction, the atoms or the molecules or whatever, they are not reacting haphazardly. They are reacting in a particular ratios, and that is what we refer to it as stoichiometry. And then this is what it is happening, and then they have asked it. Now, to do this, colleagues, we need, if they didn't tell you what is the limiting reagent from grade 11, you need to go and do it. That we need the limiting reagent here, and then we apply it there. That in this case, you are compound E, it was only 8 centimeters, so it is limiting, and then the oxygen, it was in excess. So don't let your learners be misled by the amounts. The amount may not necessarily mean the number of moles. There will be less with the one that it is 8. It can still be that one which is 50, depending on the molar mass, can go to that. So we need to address all this, and then we calculate whatever it is. So it's a shift, colleagues, that we need to look into and take it serious. That it is not only in the equilibrium table that we can use a table to calculate the Kc, but the same principle, because it's a reaction, it can be at any other part of this particular reactions that we are having, that it is going to be there. Hence, we put this under the alkanes. It's a combustion reaction, but the way it was asked, it was not only about how it is a different story altogether. So when we deal with the reactions, colleagues, let us be careful. It's a reactions, but they can appear in any form at any other point. Now, colleagues, with the reactions, other than that, next slide, Ntatenamban, it is to say, colleagues, before you go, please, colleagues, before you go to the charts, the flow charts or flow diagram, let's our learners get grounded with these slides. Examples are there for you to develop other. So we cannot just give one reaction. For alkenes, for instance, where we are reacting them with chlorine, whereas they are expected to do all four. And in all four, there are conditions which are there. So for our learners to know these conditions, colleagues, because it's where the problem is, it is not for us to know, not ask them about these parts or the conditions repeatedly. We have to ask them in each and every assessment that we are having. A reaction, it is having condition under which it is occurring. So we have to ask them and not only go to the flow chart and answer the flow charts. Flow charts are there, it is fine. But in all the other, you can go to any other baba of what we are having, and the slides, it is all about that we need to do everything, and each and everyone must be treated fine and well. Just before we go out of that slide, Baba, there is a reaction of bromine, which is bromination. It's an experiment, colleagues. So please, colleagues, let's do that reaction. So here it is going to be on addition, but what is going to happen if it is an alkane, because there is something that is happening when it is an alkane. So that particular part, colleagues, is part of the reactions that we are having. So please, let's go and do it and not just leave it just like it is. That we are not doing those experiments and then we are satisfied that everything it is not correct. And if we can do that experiment, colleagues, please play a video for them to can maybe get to the gist of what it is expected. So, colleagues, when we visit you for the reaction of alkenes or whatever, we want to see all four, with the condition being as not only the products and the reactants. We also want to see this, and not only the question as they are in the exam. Adapt those questions as you outsource them from exam type questions to go and address all this, because remember, in the exam, the examiners are asking limited questions because there are certain amount of marks that they need to do, but they are leaving a lot unattended to. So it is important that for those where they didn't ask, our learners also are covered and then they have asked what we have. Can you go to physical properties, Baba? We can move, Baba. Uh-huh. Here it is, one of them, colleagues. This question this question on physical properties. I want us to look at how it was asked and what is it that we have to learn from it. Just go to the next slide, Baba. Colleagues, here it is. The following are vapor pressure of these compounds that are given at a given temperature. Compound A, it is having this amount of vapor pressure, and compound B, it is given this. Colleagues, write down the structural formula of compound A. Now, it's fine, no problem with this. But look at number 2, IPEC name of B. What we are saying is, if they've given the structural formula of that, let it also, they must give us the name of that one, into which homologous series it is. Also, can they draw the condensed structure of that if they can get it? Number 2, the same will go for this one. So this 4 marks, colleagues, we are saying just stretch it a bit. Now, this there was no problem in the question. The whole of this was no problem. But we want to learn from this. What is it that we want? I want to look at number 3.6. The boiling point of compound A is measured against one another when that is matched. How will the boiling point of compounds now be affected? Choose from decrease and increase, and then it is one mark. Why is it 1 mark? Is because the marks were just there. But expected out of that was explain. So that is where we want us to explain. What is it that we are looking for to explain, which is going to go to the next slide, Baba. And then we want colleagues to can get this, because for physical properties, remember we're looking at different scenarios that we are having. What is it that we have seen our learners struggling with? Surface area, branching, intermolecular forces, energy required. Then that is where we are looking at. And then we have put some few things that we want us to look at before the colleagues can go. We can go there, but then that is the next slide that we are going to do. So we're not going to do this because that last part, it is only 1 mark, but in most of the cases, it is more than 1. Now I want us to look at these 2 structures, colleagues, and try to see what is it that we see. If we look at the 2 structures, both of them are having 2. They're having 2 carbons, both of them. But now, I'm putting to you that the investigation, or if ever we are to calculate to do this, then this is going to be an invalid question, because remember, when you do physical properties, they are based on experiments. So in experiments, there must be variables which are there. So if we're having this, even though they're having two, and then they're coming from two different homologous series, of which they can be asked, but this is not going to be a fair question. And we are saying to you, even though we are going to set your own question or we are extrapolating from the tables, please take care of that. The mass, they must be at least comparable. The masses of this that are not going to be comparable, we can see already. This is already giving 32 plus another hat here, which is 12, and there. This one is going to be far heavier than this one. So the masses are not comparable. So we cannot do that for that. Different homologous series or different functional groups, it is fine. But because of this, we are having different functional groups and the mass, it is also changing. Then we are having more than one independent variable. Question is, if this was valid? No, it was not valid, because we are having more than one independent variable. We can see the mass, it is increasing, and this one, it is not. So we are saying also, try to talk to these factors that are affecting the rate of reaction. So one of them, they're coming from different frictional groups, so the energy required is going to be not the same. So that is one thing that we want us to look at as we move forward. Now, can you go to the next one, Baba? Just click it once. Again, one. Thank you. Now, colleagues, can we have a look at this? These are in the same homologous series, and we can see both, all the three are representing a primary haloalkane. You can see that it's a primary. Now, what factor was this? Yeah. If we're having a table moving from there to there to there, what factor was this affecting the boiling point or melting point or the vapor pressure of this, if this is going to be a gas? Which factor will this be? Colleagues, anyone who is very brave? Anyone who's brave? No one. Okay, colleagues. It's on the chart. And Mr. Namban, help us. Okay. Okay. Okay, Baba. Just like one. Uh, just push a button. I think, colleagues, here we can see the number of carbons are increasing. So that means it is going to be a surface area, or it is going to be a chain length. Okay. Can you go to the next one, Ba? And we want to differentiate between the two, or between the three. Now let's look at this one. All of them, they are alkanes. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Now, in this case, colleagues, can we still say this is a surface area? That we can't. So, colleagues, we need to address this and this, because our learners are just missing these two. As we move from this one to this one, you can see this length of the carbons, they become lesser. We agree. But there is this factor here that is coming in, which is branching. So here, this is becoming more branched than the rest. Now, when we compare this, we cannot talk to surface area here, because the factor, it is branching. We cannot talk to branching and surface area. We have to have one, colleagues. So the factor here, it is branching. And let's, colleagues, please do that one and help us to do it. Next slide, Baba. If colleagues are happy with what I have said. Now, let's look at this one. The same. And then I want us to look at this, where the learners, they were to say is this one and this one chain isomers? Then I would say the first one, if we are looking at this, we are starting with this one. In this one, colleagues, the double bond, the position of the double bond is between carbon 1 and carbon number 2. And then when you go to this part where we are having the branches, the position of the branch, it is at number 2. So the position it is 1 and 2. The positions have not changed. Of what? Of the substituent here, it is still at carbon number 3 for this one, and then this one it is still at carbon number 1. So here and here we didn't change the position of the substituent. So this one we have just increased the length. So this one and this one, they are going to be chain isomer because we have increased the chain. I hope we are okay with that one. Now, why is this not a chain length? A chain isomer. If we start with the same as that one, it is the same structure. It is still at position number 1. Now, what has happened? We have now increased the length to that one. Okay, so that it looks like that. But now look what we have done here. We have now changed the position of the methyl group. It's no more at what? At position number 3. So we have changed this one there. So this cannot be a chain isomer of this one because it is two things that have changed. It is the chain and also the position of the methyl. So the learners will get it wrong. But if we are looking at this one and this one, the chain length is the same. And then here it is the same chain length, but we have moved now this one here. Then it is going to be the position of the methyl group has changed, and it is going to be isomer to that one. But of what type cannot be a chain for one thing for sure. So colleagues, let's look at why it is a chain length and why is this not a chain length. Which factors are we looking at and why? So let us not just leave it to the learners who can say this is going to be what it is and not what it is. So, and also colleagues, let us not try to be very soft with our learners. If they're getting things wrong, let them get it wrong and address it, why it is wrong. So addressing it what is wrong, then we are building on their conceptual understanding of what we want them to understand. Next slide, Baba. Next slide, it's fine. It's a multiple choice question also, colleagues. The organic compound that is converted to an alkane as shown in that, but now you see the alkane, it is not there. It is just an alkane. There is nothing. So here we can see we are moving from one homologous series to the next. It's a reaction. What is going to happen? Now look, which of the following catalyst is going to be suitable? If the learners from that table that was given to them, they didn't get it, then it is going to be a problem. So the one that we are using, we have never used this any other except for platinum for that reaction. So it is important that they recall it. It's a level 1 type of equation for that. But other than this, colleagues, what is it that we have? The type of reaction, what is it that we could have asked? And what is the other reactant which is there for it to the alkenes, and how we go to that, breaking the double bonds and explaining everything about this will help the learner to understand the reaction of alkenes going to the alkenes. What is it that it is happening? So it is another way of putting the question and not just as a flow chart. So we are moving in that direction, and colleagues, please let's try our best to move into that in that direction. Next slide, Baba. Now, colleagues, flow charts, they can be there. or the other form can be this one. So this is another way of putting a flowchart. Now, what are we saying? It's we have been given the flowcharts all along. Can we go from one step on the flowchart and come up with actions that can be put in the same way as this one it is put, and not for the learners just to see it for once, or the one that was already in 2020 2024. Remember, if you give to them as an homework in 2024, some of them will just go to that memo and put it. So sometimes in a class, just put something that we didn't have. Just put it in that form instead of being a flowchart and ask the question, whatever we are saying. So in this slide, we are saying, if we don't have this form, go to the form of a flowchart. If it is in the flowchart, go to this form and expose the learners to as many as possible the answers. You don't need new questions, colleagues. We have the questions in our textbooks. We have this, then just do whatever. But the same will happen. These questions, they're asking names, IUPAC name of formula, that. But if you look at this question, no conditions were asked. So, colleagues, if you are using this, try to put more of the conditions, whatever it is possible, to reinforce the conceptual understanding and the factors that we need. It is going to help us to do better than what we are doing just now. Next one, Baba. Continuation of that, but the question it is about all this. So compound W can be converted in one step to that. You can reverse if it is reversible, that, and then you go there. State besides heat one other condition for the conversion. So we need these conditions, colleagues. We cannot do it anyhow. We need to do that. Now, for this one, it is cracking, colleagues. And cracking, it is one of the issues that we are not getting it right. And we want to appeal to colleagues. Do it. Do it. The cracking that we do, it is thermal cracking. So state one change besides temperature. You see, now they're changing. Besides heat, besides temperature. That means they want other conditions which are there. So if we are not treating this at high pressure and whatever, we are not going to get it right. So assessing conditions will always be there. Rather, the structural formula for this, where do we expect this? It's a reaction. But where do you expect this to be? It is in question number 2. So anything is possible. The same question, colleagues, you can take it and try to adopt it to what we have, because we are still having this compound X. The gas is a gas. So this gases, and it is 2 times that, you can still go and do the stoichiometrical calculation instead of taking it as it is, like we have done in the previous question. Expose them. It's a reaction. We can put that, we can ask them to draw structural formula, we can ask anything about this. All it is there, colleagues, for us to can improve on what we had, and then maybe we will get it right. Baba, next one. This is for information for the teachers, I think. For those who didn't get it, Tate Nambani will help us. This is the information. Okay. Uh, second last. Yeah. Mm. So this is the information that they should give in that cloud space. And the next one, Baba. This one, colleagues, the assessments, especially when we are dealing with the table. The questions say compare from A to C. Now, if it's say that is in physical properties, I just cut it down. That if we are saying from A to C, between A and C, there is a B. So when we do that, it cannot be right to say we are only going to go for A and we mention the C, not mention the A, what happened in A. So you must also include that B in that, if they're mentioned there, we have to do it. And advisable is to say, start with the one in the middle. Let's say the one in the middle, it's a ketone, and it's an alkane, and then this is an alcohol. What we're going to say? With the ketone, the intermolecular forces, I'm just taking an example, of this one are weak. So we'll put that the strength for a ketone at B, it is weak. Now we have to go to A. How B it is in relation to A, then A, because an alkane will have the strength of it that weaker than that of B. There's a comparison between A and B. And then what happens to the C, which is an alcohol, then it is going to be stronger. So we can see on the comparison, we have tried to match all three because we started in the middle. And we avoid this thing of saying from A to B, this is the strength of the intermolecular forces as they write it. And from B to C, it is this. And then A to, so that story in the table, we encourage the table. So, but the comparison, they must be there. The type of molecular forces, or maybe when, okay, let me put it before I go there. Now, our learners, what will be they saying? They will be saying molecules of A are strong, but they're talking to the strength of intermolecular force. It's not the molecules, but it is the intermolecular forces. So we need to stress that part, that colleagues, it is important that we talk to the contents of this table or the heading on the table. They must be correct. And then the learners, they must correct whatever it is inside that particular table. Now, Dr. Nambani, this is what I've seen also, that in the ATP, in the free state assessment guideline, they can look at it. That bullet number 2 for week 4, it is somehow misleading. There is no bullet after, I think, starting with resolution of vectors. Okay, that is talking about the components. Just before the component, there must be an enter to can come up with a bullet. Colleagues, remember when you draw free body diagrams, we said are not accepting the components. So there it is just talking, drawing the free body diagrams and then components of that indicate the forces and the components. No, we have to rectify that, and then just before that, just put an enter so that at least we are not talking to force diagrams having the components of the forces there. I think that's all that I wanted to say, Tate Nambai, and thank you very much. And the last one, Baba, the last slide just before this one, and then I hand over to you. That is the closing slide. Yeah, that one, and thank you is the next slide. Thank you, Baba. I think colleagues are aware that colleagues, the formal experiments, we are not splitting them anymore. It is one worksheet of minimum of 50 marks. No tests, no nothing. It is formal experiment. It is going to be a worksheet or a formal experiment. Now, because it's a formal experiment, it's an SBA task, colleagues. You cannot take it and give it to the learners to do it at home. It must be under supervision of the teacher, just like a test or any other examination, because it's an SBA component. So we are running the risk, colleagues. If we are taking to the learners and then you go and help them to do it at home, then it's a good recipe for SBA rejection. So we are appealing to you, colleagues. Let's respect the SBA tasks, because this is one of them where we are going to have a problem. So the dates for the control tests are as indicated there. The grade 12 is on the 19th, grade 11 is on the 20th, and grade 10 is on the 23rd. So please, colleagues, let's already start doing the experiments. Formal experiments are prescribed experiments, and they can be asked also in the form of a task which is written as an examination or informal task form that they can have, examination or control test, because they are prescribed, they must be done, colleagues. The other informal one, we still have to do them because they're in reinforcing what we have as colleagues to help the learners. And then the next slide, number, it is closure. Thank you. And thank you, colleagues.
No, thank you, Ndate Nambane. Thank you very much, Ndate. I just want to say to the colleagues at NTSIE, good afternoon, colleagues. Thank you, NTSIE, for the well-detailed presentation and your emphasis on the topics of term one and the things that we should really expose our learners to. And most important, thank you, colleagues, for the sacrifice, colleagues, that you have been in this meeting for almost 3 hours. Without you, colleagues, we are nothing. Thank you very much for your attendance. Siyabulela, re a leboha. Thank you, Ntate Nabane.
Thank you, Baba. Goodbye, colleagues.